worried. I added 12 points to everybody's test, if you didn't already hear that. So I didn't put it on there. So whatever score you got, add 12 to it. Is the grade that's in the grade book. No. That's your actual score. In my grade book, I added 12 points. Because that was after I did it, and I just didn't feel like going back and rewriting them all. So your scores are there. If you got over a 90, including the 12 points, you are still on pace to being able to possibly get out of the final exam. If you didn't get that, you're going to have to take the final exam, which is fine. The final exam can replace one of the lowest test scores. So if you get better than your final exam than the test you just took, you'll replace it with that one. So that's a way to improve your grade as well. Yeah.
How do you calculate?
I do it because there's many different ways to calculate a curve. If I calculated a curve based on just putting the highest person up to 100, which some teachers do, you'd have gotten screwed because you'd only gotten 2 points. So what I typically do is I want my average to be a 75, 76, right around there. That's what I want my average as I test to be. So if my average is lower than that, I will typically add points to get it up to that. That's what I did. My average was a 64. I wanted a 76, so I added 12 points to get it to the 76. That's how I typically do my averages. And amazingly, as crazy as it sounds, I've not had a test average higher than a 79 in all the tests I've given. So I've never had to go the other direction, which I probably wouldn't either way. I try to create my tests so they're right around there. So this one turned out to be a little harder than that. So I make it so it's about the right thing. So no.
So this is wrong, right? It's the other way around?
Yes.
Okay.
Yes. Which is a very common mistake on this test. A lot of people did the other direction on their integrals, especially when they did the integration by parts. X became 1 on quite a few people's things. All right. So
me up was like when you said there's going to be one question that's going to look one way is going to be a substitution.
Yep.
I did it the other way.
Yep.
Later I found out.
Then you realize it was like, oh, yeah. 8. Question 8 was the substitution one that it was the actual trig substitution problem, which I eliminated because I knew how hard that one was by making it a U substitution, and more than half the class did it the hard way. I tried. Yeah, yeah. So it is what it is. All right, so we looked at arc length on Tuesday. And the arc length formula was it was the square root. Actually, it's right here. It's that 1 plus the derivative of f of x squared. And the square root of that. That's the arc length formula. So if we're going to look at, when we looked at volume, we took the pieces inside and rotated them. If we're going to look at surface area, it's really just the outside edge rotated. Okay, so that's what we're looking at tonight. We're looking at the surface area, which is your arc length rotated around an axis. Every one of these problems that we're going to do tonight, and any problem that I'm going to put on a test or anything else, will be rotated around the x-axis or the y-axis. None of these will be shifted. It makes your problems insanely difficult if they're shifted. So they will all be rotated around the x-axis or the y-axis. Okay? So if we're going to rotate it, all we really need is the circumference. Now, circumference is 2 pi r. 2 pi times the radius. So when we're rotating it, we need the arc length and we need the radius. The 2 pi is just going to stay there. So 2 pi, your radius is just going to be your function. Okay? Depending on how it's solved and where it's rotated. All right? you're going to see if it's solved, if we're rotating it like this example, we're rotating it around the x-axis. My radius is the function. If I was rotating it around the y-axis, my radius would be just x. It wouldn't necessarily be the function. It would just be x. And we're going to look at a few of those in a minute. But in essence, this is the formula you need. That's it. We're going to simplify it a little bit because we're going to take dark length and basically do that part first and clean that up as much as we can, and then just plug it into this. The other nice thing is, and quite a bit of these problems, remember our problem we were doing with arc length when we had to do the trig substitution, those problems was we didn't have something on the outside to do U substitution. Because now when we're doing surface area, we have something on the outside. So U substitution becomes quite often a way we can go with it. Because we have something that when we do the factoring or make the U substitution, we have the other piece that we can cancel it out with. So that's going to make my life a little bit easier. All right. Let's do one and see how it goes. All right. So my curve in this case is y equals the square root of 4 minus x squared. And we're looking at it from -1 to 1. And it's rotating around the x-axis, as you can see in the picture. I'll make it a little bigger. So remember, the equation is the integral from a to b of 2 pi. The radius, which in this case is y, because that's my radius. The square root of 1 minus the derivative of y squared dx. And I could go, well, I have y's that are doing dx because we're going to replace those y's in a second. Yes.
Why is it 1 minus?
Was it 1 minus or was it 1 plus? Oh, it was 1 plus, sorry. I got stuck with the minus in the problem. All right. So now we just got to find our stuff and plug it in and do my integral. So we're going from -1 to 1. It is symmetric. If you look at the picture, it's the same on both sides. So we can do 2 times and go from 0 to 1, make my life a little bit easier. And then we have 2 pi times this fourth, or the square root of 4 minus x squared. And then we have 1 plus, and we need to find the derivative of that. So how do I find the derivative of that?
Is that trig sub?
No, that's if we're going to do the integral, yes.
Oh.
Derivative. We have to do the chain rule for this one. So I can change this one to 4x squared to the 1/2 power. So I bring down the 1/2. I mean 4 minus x squared to the -1/2 power. And then the derivative of the inside is -2x. So this will be negative x over the square root of 4 minus x squared. So I could put that in here. Squared. So the derivative of the inside is negative 2x. And then I have the 1/2 out in front. So that's where the negative x came from. And then the for that to the negative 1/2 power, that just brings the square root down the bottom. All right. So is everybody good to that point? All right. So now I got to do my integral. So this is where I was saying you always want to try to work on cleaning up that big square root problem as much as possible before dealing with things, because that's where the mess really is. So let's work on this part here. Clean that up. So I have now 1 plus x squared over 4 minus x squared. So I just squared the top and the bottom. Negative x times negative x is positive x squared. That's where the negative sign went. So now let's take this and let's get it as one fraction. This is where all that algebra comes into play and how to manipulate things. So I have 4 minus x squared plus x squared all over 4 minus x squared, which ends up being 4 over 4 minus x squared. So that right there is that. That's the 1. That's where the 1 went. And now this whole thing was the square root of that. So that ends up becoming 2 over the square root of 4 minus x squared. All right. Any questions with what we've done there? Because in a second, this problem is going to become really, really, really simple. But if you don't understand how I got to there, you won't understand why the problem becomes simple. Okay. Everybody good? All right. So I'm going to pull out the 2 pi, so I have 4 pi. Square root of 1. And then I have square root of 4 minus x squared times 2 over the square root of 4 minus x squared dx. So these two things right here cancel completely out.
Did you have the
That too? Yes.
How did you get it to work?
Because
Why is
I did it from 0 to 1. I used symmetry to get it from 0 to 1. Oh, that would be why. All right. So now actually I can now pull out that 2 because it's a constant, and I have 8 pi integral from 0 to 1 of just 1 dx. What's the integral of 1? I mean, yeah, what's the integral of 1? It's just x. So it's 8 pi times x going from 0 to 1, which is just ends up being 8 pi. So you can see how doing the algebra work and trying to simplify down the problem as much as you possibly can helps with these problems. Because if you tried to do the integral on this thing up here at the beginning, you'd still be working on it tomorrow. That is just going to be an utter mess to try to deal with, because you'd have to do the product rule and it'd be a mess. So you really have to simplify down the problems as much as possible. In essence, that's all we're doing tonight. We're just going to do a bunch of these problems, but that's it. That's the only rule you're going to learn. It's just basically that one formula. The only difference you're going to have is determining if your radius is the function or if it's x. And
If
that's
it's a function or what?
if it's x. And it's really depending on what you got and where it's rotating. So in this problem, my function was my radius because I was going from my function to the center. So that right there is y, which is my radius. If I was rotating around the y-axis.
Oh,
And we're going to do one like that right now. All right. So now we've got this shape. So this is the parabola. It's y equals x squared. And we're going from 1, 1 to 2, 4. And they're rotating around the y-axis. So in this case, my radius is x. It's not, we're not going up to the function. We're not looking at the y going up and down. We're going across. So we're going to the x value. Huh? No. Well, okay. You could do it that way if you want and solve it for x. You do not have to. Okay. So if you remember when we did the arc length, the formula was basically exactly the same. It was just depending on which way the function was written. So, and actually, when we're looking at this, we can find the arc length of that with y equals x squared. We don't have to change it over, because nothing in my formula told me the direction I was going. It just said where you're looking, starting, where you're ending. So I could still start at 1 and go to 2, and I would still get my arc length of that line, which is all I care about when I'm rotating. Okay. So you don't have to solve this to get x equals. We can actually just use the radius as x. My function is still going to be f of x. When I plug it in, I'm still going to do the exact same process and everything else there. Okay. So changing it over actually is going to make your life harder in this situation. Should still get the same answer, just more work. So let's set it up. Since we're going around the y-axis, we're going from 1 to 4. Actually, I lie. Because we're using the y equals, we're still going from 1 to 2. Because the equation solved, we're plugging in for the x, so we're using the x values. Since we're plugging in for the x values, because my equation is still y equals x squared, we're still using x. We're not solving. We're not plugging in for y, which is if we were plugging in for y, I'd go from 1 to 4. Since we're plugging in for x, we're still going from 1 to 2. Yes.
But you can still use the radius value.
Yes. You're still using radius as x.
And then so the arc length is just make it as easy as possible. So you use the y.
Yeah, we're going to plug it in just as x squared. Well, the derivative of x squared. So my formula is going to be 2 pi. My radius is x. And then it's the square root of 1 plus. And it's still y prime. So if y is x squared, y prime is 2x. So it's 2x squared. Mhm.
Why do you by x and I are x squared?
Because that's not the function. That's just x. And the other one, so the radius is where I'm going from the axis to where I'm going. So in this problem that I just did over here, I was going from the x-axis to the function. So that's why I did the square root of 4 minus x squared, because over that range, the 4 minus x squared was what changed. So my radius changed that direction. And this one, I'm going from the y-axis out to the function. So the value that's changing is not my y, so it's not y equals x squared. The value that's changing is x. And it's changing from 1 to 2.
Why isn't it a function? Because the x is constantly changing.
Right, but it's changing based on the x. It's changing at all values from 1 to 2, which is what my integral is telling me.
So you don't have to put
Okay.
it in terms of y then.
No, that's what I'm saying.
You want to solve the other part. In terms of, but you in a case where it's easier to transfer over to like using y's in the problem.
You could.
Then
And then you would plug in, so if you solve this for x, so you got x equals the square root of y. That would now be the square root of y.
Okay.
And that would be the derivative of the square root of y. And you could do the exact same thing. The only change would be is that now it's going to be from 1 to 4.
All right.
Okay. So you could do that. It just depends on which is easy. And this one, this way is way easier than doing the others. Okay. But it really is depending on which way you want to go. And you could actually do the same thing rotating around the x-axis. If it's easier to solve for x, you could do that too. And it would end up being y and then whatever y was inside. So you have that option actually. Yes.
So we use y in the other one. So the y equals is just a function of,
Yes.
and we use it as the y in the other one because the function of the curve is based off.
Yes. So that's why we use that there, because that was the radius. The radius is changing based on that function. In this case, the radius is changing based on the
Y
x.
equals X is still it's
So,
still
yeah,
the curve,
but it's not the radius. Okay? Copy this already? All right, so now let's clean up my inside a little bit. And we can pull out my 2 pi. So this just becomes 2 pi, the integral from 1 to 2 of x square root of 1 plus 4x squared dx. That x right there is really, really nice. Because of that x, I can do u substitution. So u is 1 plus 4x squared. And du is 8x dx, which is 1/8 du equals x dx. We'll go back. It doesn't matter in this case. All right, so I have my 2 pi, 1 to 2. The x is gone. I have 1/8 left over here is the, I'm just going to actually do u to the 1/2 du. So it's the integral of u to the 1/2. Yep. And we're evaluating that. Well, I got to plug back in the thing first. All right. Questions with what we did before we actually come up with the final answer? All right, so this one is, pull out 3/2. So I've got pi over 6. And then it was 1 plus 4x squared to the 3/2. And we're evaluating that from 1 to 2. So if I plug in the 2, I get 16, 17. So it's 17 to the 3/2 power. And then if I plug in the 1, I get 5 to the 3/2 power. That's the final answer. Since you asked, and I don't feel like writing it all out. And I have it in the book. I'm just going to show it to you from the book. All right. So if you wanted to switch it, you wanted to solve, so we're rotating around the y-axis, you want it in terms of x equals. So x would be the square root of y. The derivative of that would be 1 over 2 square root of y. Okay? So we plug in just like we were doing before. So we've got the 2 pi. Since we're doing the y's, we now go from 1 to 4. The x is the square root of y because that's what x equals. And my derivative was 1 over, well, the derivative was 1 over this 4 square root of y, or 1 over 2 square root of y. So when you square it, you get 1 over 4y. All right, so since they're both square roots, you can put them together. Yeah, this is the other way. So they put the square root of y and this thing together, so that's how they got the y plus 1/4. Because y times 1 is y times 1 over 4y is 1/4. They pull out the 1/4. You don't have to. Because at this point, they basically just do the u substitution. And you could do the u substitution with the 1/4. So they do the u substitution, and it comes up to be the. Now, we can do the u substitution here because the y's disappear. Because it's not y squared, it's just y. So we don't need the y or the x or anything else on the outside of that situation. And it comes up to be the same answer. 17 squared to 17 is the same as 17 to 3 halves. Okay. So either way works. It's just a matter of which one is easier to work with. It's just like the disc and the washer method. Both of them work. The nice thing with this one is it's in essence the same formula. Right? The formula really doesn't change. It's the radius. It's just depending on which direction your radius is going. All right. So I'll write the equation and you guys are going to set it up. So we're doing y to e to the x. It's from 0, and we're rotating around the x-axis. Oh, because I forgot to switch over to the tab. There you go. So y equals e to the x. We're going from 0 to 1, and we're rotating around the x-axis. So set me up my equation. Or my integral. All right, so what's my integral going from? 0 to 1. So 2 pi. What's my radius? Yes, my radius is e to the x here. And then we have my, what's the derivative of e to the x? E to the x. So I get 1 plus e to the 2x if I square it. dx. Can I simplify that anywhere? No. And if I did u substitution, u is 1 plus e to the 2x, and du is 2e to the 2x. And I only have an e to the x on the outside, not an e to the 2x. So even u substitution doesn't work. There actually is no way that you know how to integrate that.
Is there a way to stuff, huh?
Huh?
Is there a way?
There might be, but this is why we have computers. But we can't even use trig substitution because it's not x squared. So you'd have to make it would end up being e to the x is your thing there. And because it's e to the x squared, not x squared, and you can't use, it's got to be just the x value in the trig substitution. All right, so we're kind of stuck on this one. Let's try the other method. Let's see if that works. So we're going to do the same problem, except this time we're going to use the other way. So instead of y equals e to the x, what would x equal? Ln of y. And then x prime would be 1 over y. All right. So this does change too because we have to do it in terms of the y. So it would be 1 to e. Anybody? Okay, maybe I should ask it this way. Does anybody know how I got 1 to e? That's why I asked the other question. Because if I asked how I got it, like if I did, does anybody understand how I got it? Most people said no. How do you get it?
So it's e to the x, each 0 is 1 and then 1.
Yeah, I just plugged in those values for e. So, all right, so we've got our integral. It's still the integral of 2 pi. This time it's just the y. Then we're going from 1 to e. And I have the 1 plus 1 over y squared dy. So if I try u substitution here, I make that 1 plus 1 over y squared. So du is -2 y to the -3rd power. Still doesn't get me anywhere. So the question is how do we do this? Believe it or not, it's kind of funny. You cannot do this on the Desmos scientific calculator. You can do this on the Desmos graphing calculator. I don't know why. I just don't think they've put the actual the functionality into the actual scientific calculator yet. But you can do integrals, definite integrals, just like this, on the Desmos scientific graphing calculator. So, go to Desmos graphing calculator. If you click the little piece down here, if you go to functions, there's the integral. It's a little bigger. And we're doing this from, it was 0 to 1 originally. And it was 2 pi. And it was e to the x. And then it was square root 1 plus e to the 2x. Why doesn't it confuse me? Oh, well, I forgot the x at the end. There we go. So it'll give it to you as a decimal answer. So the surface area for this one is approximately 22.94. Yes.
Just the way you want us to do it, book shows a different way.
No, actually, the book showed the exact same way. Depending on, it's example 4 in the new book.
I feel like we had bigger speed around it.
Do you know how the computers figure out integrals?
Yeah, it estimates it. It breaks it down and does the Riemann sums. So remember, integration and derivatives and everything else like that is just getting infinitely close. It's a limit. So the calculators are doing the limit. It can put in higher and higher numbers to do it, to actually get it close enough that it actually does the approximation of it. It's not giving you the exact answer because it doesn't know the exact answer. It knows approximately what it gets to. That's what it's doing. No, it's the same as example 4.
I haven't seen the problem, but it's same example. I'll show you later.
Okay. Okay. I'm like, 'cause I'm looking at it, like, and it came out to be the same answer, so I know I typed it in right. So yeah, it just, that's, unfortunately, there's some things that we just can't do by hand. And yes, there are ways to do it. There's ways to do technically any of them. A lot of them, more of the complicated ones, ends up going back to a limit where you're looking at approximating a value that way instead of getting the exact value. Which is what I just said the computer does here. If you have the TI-89, the Inspire, those calculators can also do integration. That's why most calculus teachers don't let you use those in class, because it'll give you the exact answer. All right. Let's now do one that you actually can do. Do this one. So write me my equation first. Start there. No, it's x to the third over 6 plus 1 over 2x. Then it's a comma. It's 1/2 to the x, or to 1. All right, so that's what you should have for your integral. Yes.
Biggest problem with these questions is I don't know when to put y in terms of radius or the value of y. How will we figure that out? When to put y or
Where are you rotating around?
this x-axis?
Yes, we're going around the x-axis. So one of the options that you have is to graph it, but I'm gonna graph it so you can see it, but you shouldn't have to graph this. But it's easier for me to show you what it's graphed. We're doing it from half to 1. All right. So there's the tiny little graph. All right. So that's basically what I'm doing. And I'm rotating it around the x-axis. So my radius is coming from the x-axis up to that. So what's over the range from negative, or the domain from 1/2 to 1, the radius is changing based on that function. Okay. So I would use the function. Okay. If I was going around the y-axis, the radius would be changing from here to here based on the x, not the function. It's still going from 1/2 to 1. So my x values would be changing from 1/2 to 1. My radius would be changing from 1/2 to 1, not based on the function that I have. So when you're looking at how it's rotated, that's how you determine its radius. So if I'm rotating this, I'm going to actually stretch this a little bit. If I'm rotating, so I'm rotating around the x-axis. Okay. So from 1/2 to 1, how is my radius changing? My radius is changing based on that green line, which is my function. So in my radius, I'm going to put what f of x is over y, the equation. If I was rotating around the y-axis, my radius is going to here, from here to here. My radius is changing from 1/2 to 1, not based on that function. It's going to hit every value from 1/2 to 1. So my radius is x. Okay. So the easiest way to recognize it is, it's always you're rotating around the x. You want it, if it's in terms of y, like y equals, you put the function. If it's in terms of x equals, you put y. If it's rotating on the y-axis, if it's in terms of y equals, put the x. Yeah. If it's in terms of x equals, you put whatever the y is. You put the function. So they would switch, yeah. So like this one, I'm plugging in the equation. I'm going to have the function there. So when I wrote this one, that's why that function's there, because my radius is changing based on that function. The radius is a height in that case. So it's based on the y. Yeah.
It's a suggestion. We create a slide where you can sort of summarize what you just said, where you have a line going up to the radius and saying around the x, the formula, so half the distance for the y.
Yeah, give me a second.
Be the position. I think that's what I'm getting. Would it be easy to just do it like a?
There's another way I'm going to write this one. Okay. All right, so it's integral. All right. I'll make sure I get this one right. Yeah, that's dx. So you can use any of these interchangeably. Okay. There's in essence 4 different ways that you can set up this equation. All right. You can do it any way you want. You can mix and match. It's just a matter of what your radius is, which direction you're moving. Okay. So this ds is just one of those 2. So if your problem is solved for the x, you're going to use this dx. If your equation is solved for y, you're going to use this one. Okay? Simple, straightforward. If your equation's rotated around the x-axis, you're using this. If it's rotated around the y-axis, you're using this. Okay? Period. Does that make sense? Or no? So this is x-axis, and this is y-axis. This would be y equals something, and that would be x equals something. Okay? Does that part make sense with what I wrote? I'm going to show you how to mix and match it in a second. Okay. So let's say you're rotating around the x-axis, and you have the equation solved for x equals. I'm using this and this. Okay, because it's rotating around the x-axis, and I have the equation solved for x equals. Okay? See how this is dy? I'm not changing that y. I'm keeping the y. Okay? Where if it was rotating around the x-axis and it was solved for y, that's a dx. That's got to be an x's, not y's. So I've got to replace it. Yes? No? Okay. The key is this is going to tell you, once you pick which one of these you're using, it's going to tell you what that has to be, because it has to match whatever this is. So if I'm rotating around the y-axis and I have it solved for y equals, well, I want a dx. I can leave that there. I don't have to change it. Where if I have it solved for this, well, I have a y. I got to change it to something in terms of y. Okay. That kind of helps, Scott? Okay. So for this one, we have it solved for y, and we're rotating around, this was rotating around the x-axis. Okay. So I'm using the y dx. I have it solved through a y, so I'm using that function there. That's an x. Well, it can't be a y here, so I've got to put what y is. Because this would be 2 pi y ds. That's y, and that's the ds. Okay? Good, now solve my integral. My suggestion would be clean up the square root first. That should be your square root. So combine that into one fraction. So I just had to multiply that by x squared. You got a common denominator. And square it. So you get x to the 8th minus 2x to the 4th plus 1. And then that 1 becomes the 4x to the 4th over 4x to the 4th, so we get it down to that. Remember, your goal, when you have a square root, a lot of times what you're trying to do, especially when there's fractions and stuff like that, you're trying to figure out a way to get rid of the square root, which means you need to get it in terms of something that's squared. Okay? So I'm doing all this to try to clean it up so that I have something squared over something squared so I can get rid of the square root. Because the square root is causing us trouble. We add an x to the 4th, we get 2x to the 4th. That right there, these are both perfect squares. And if you do that out, you do get the 2x to the 4th in the middle. So now that's squared over that squared. So I take the square root of that, and I no longer have a square.
Is that x8 minus or plus?
That's a minus, that's a plus. Because negative 2x to the 4th plus 4x to the 4th is a positive 2x to the 4th. The next step you actually could do a couple different ways. So when we plug that back in, we have x to the 3rd over 6 plus 1 over 2x times x to the 4th plus 1 over 2x squared. Notice no more square root. I chose to make them just two fractions and then multiply them. You could have split this one up, the second one, back into two fractions and then just FOILed. It would have ended up giving you the same answer at the end. I don't know which, either one would be easier or easy at the end. So I ended up doing it that way, getting this. And then I broke it up into fractions in the next page. So you could have easily done this as just distributed the two fractions. So you would have ended up getting, instead of this, you'd have had that one time, or it would x to the 3rd over 6 plus 1 over 2x times x squared over 2 plus 1 over x squared, and then just FOILed those. You could have done that too. Yeah. This is where I had one thing in my mind and I just kept working on it. I was like, okay, get them together to be one fraction to multiply them. Where now after I found the answer, I go back, I'm like, oh, this way probably would have been easier. It's like, it's fine. It still works out. You still get the same answer. This way would have just saved me a step. Which part are you mixed up on? So this was this plus this squared. When you square the x to the 4th minus 1, You should get that there.
I'd probably just.
And then you can break this up. So I have individual fractions that I can do my integral of. So I got this. I didn't do the actual 1/2 and 1 yet. Because it's just going to be a mess of fractions. This one? So I took this and made this.
No, the one you got that.
Oh, this page?
Yes.
That's okay. So I just multiplied this. So I had a FOIL at the top, and then you multiply the denominators. Where? Here? No, it's 2x. Because when he took the derivative, the square root of that, it became 2x
Where
squared.
the one from your Y. Because I got a different answer.
So it's x to the third over 6 and 1 over 2x.
When you pull it, it's 2 times. 2 times x to the fourth, that's what I got.
Yeah, 2x to the third times x to the fourth.
Isn't it the 2 times x to the fourth?
Here?
X to the fourth? That's
Oh,
what-
wait. You're right. That should have been x to the fourth. You're right. Now everything changes. So that's an 8. And that's a 4. Oh, which actually makes my life easier. So this ends up being 8x to the fourth. So I've got x to the fifth over 12 plus x over 3 plus 1 over 4x to the third.
I got it.
Yeah, now I got to do the derivative or the integral of it. That should be right now, though, right? Because 2x to that's 2x to the eighth, 2x to the fourth, 6x to the fourth, 6. The bottom's still 12x to the third or 24x to the third. So divide that by 2, so it's 12, and x to the fifth, 8 minus 3. 4 minus 3 is 1. 8 over 24 is 3. And then 6 over that is 1 over 4 to the third. So if I do that, I have 2 pi. We have x to the sixth over 72 plus x squared over 6 minus 3, no. Twelve x to the squared. That's what 8. One half and 1. That's better. Yeah, it's still 1/2. It's negative 1/2. Because it's x to the negative third power, which ends up being -2 or negative 1/2 x to the negative second power, which gives you the negative 1/8 x to the second power. It's still a fraction, even though it's underneath, because you're just treating it as a negative exponent at that point. So if we plug in 1, we get 1 over 72 plus 1 over 6 minus 1 over 8. Minus, when I plug in 1/2, what's 2 to the 6th power is 64. What's 64 times 72? 4608. 1/2 squared is 1/4, so that's 1 over 24. One fourth is there, so that's 1/2.
I missed a square, and when I tried to go back, that's my answer. My solution had a lot less. X. Terms with X,
Got it.
like 3 total.
I only have 3.
Well, it's in a single fraction.
Oh, you put it. Got it.
Can go back, slide.
Mhm.
Okay, I have one answer.
All right. And yes, you can simplify that. I'm not doing that right now. This is where calculators are really, really handy. So. But it does make sense because this problem, like when we looked at the graph, it was a really small graph. And we're only going 1/2. So the surface area being quite small does make actual sense in this respect. You're missing something over here. So,
How'd you get 4608?
yeah, right there.
Get that.
60, because it's 1/2 to the 6th power, which is 1 over 64, divided by 72. So it's 72 times 64. So that's where that came from. Same thing like here. So this one's easier to understand. 1/2 squared is 1/4. 1/4 divided by 6 is 1/24. So. No, it's okay. Other than that, we're done. So